And we had also seen that how to convert your digital signal to analog, where there is a requirement of conversion from digital to analog. And this process takes place normally in your communication system, where there is a transmitter, you convert analog to digital conversion. Where there is a receiver, you convert your digital signal into analog, so that user and receiver can communicate each other, right? And we prefer to choose analog communication or analog signal processing where there is a requirement of accuracy. Whereas in case of digital, you miss out the accuracy part, and there are some critical places where the accuracy is prime concern. Right? Considering these factor in our mind, and then we start to discuss how to build the analog circuit. So, and we had also seen that what are the different second order effect that a MOSFET can faces during the operation of your analog circuits. And there are three different type of second order effect that we had seen. The first one is subthreshold conduction. The second one is your body biasing effect. Third one is channel length modulation. We'll continue the discussion further to discuss channel length modulation and then other essential parameters that we need to understand before discussing or designing actual analog circuits. Right? So let's start with IV characteristics of a MOSFET, and then we'll make MOSFET as a current source and how the channel length modulation helps us and how to start building an amplifier. Okay. So if I draw a characteristics of a MOS transistor, especially N-channel MOS transistor, then what you can see is that this one. So this is a plot of your ID versus VDS. Right? When your drain voltage is increases, and then your drain current increases linearly, right? And at a point where the current is going to start saturates, right? So this plot is normally referred to be kind of parabola where your current is linearly increasing, and you can call it as a linear region of operation. And when the current saturates, or you'll get the constant current, and then you are entering into the saturation region of operation. And this current is a maximum one when the current is saturates, and you'll get the current as mu n, half mu n COX W by L VGS minus VTH whole square. So this is the current that you'll get at the maximum current. But before that saturation region of operation, you have a linear increment of your current as your VDS value increases, and this is a point which is referred to be VGS minus VTH. Means it is the boundary region of your linear and saturation. Right? Okay. Now if you write the same expression once again here, which is ID equivalent to half mu n COX W by L VGS minus VH whole square, and this is the current when you are under saturation region of operation, right? And the condition for saturation region of operation is that VDS is greater than VGS minus VTH. And you have the linear current, which is the graph which is depicting in our above figure, that which is mu n COX W by L into VGS minus VTH into VDS minus VDS square by 2. So this is the current that you're going to see when your device is under linear region of operation. Okay, and the condition here is that VDS is less than. So now in case of saturation region, VDS is greater than or equal to VGS minus VT. Linear, VDS is less than VGS minus VTH. Right? So this is what you can notice. Now if you notice this linear curve, because we are interested to know the linear current increment with respect to the increment in your VDS. So we are interested to identify this region and then want to know what is the current and then variation that takes place in your MOS transistor. So what you can see here is that if you look at this complete expression in the linear region of operation, this term is common for both VGS minus VTH into VDS and VDS square by 2. So you have a two terms that you can explicitly write. This is the first one and this is your second term, and this mu n COX W by L is a common for both. When VDS is much less than VGS minus VTH, then what you can do is you can neglect the second term. This term can be neglected, and then you're going to have the current in your device. What we are trying to say is that VDS is much less than VGS minus VT. It means that you are talking about the region somewhere here. I mean to say that the region that we are discussing here is that this region means VDS value is much less than VGS minus VT, and there is a point which is VGS minus VTH, and you are much less than that, means well below this region or well below this value of VGS minus VT. So we are talking about this is a region where your VGS minus VTH. So what you can notice from this equation and graph is that when my VDS value, if VDS value is less than, what I can say is that the first term and second term here. So if you consider that the second term is much lesser than the first one, or VGS minus VT, then you will get the linear relations, right? That is your linear current increment in your device. So what you can do here is that if VDS same, you can cancel the VDS term, one VDS here, and then one VDS here. So what you can have is that VDS by 2. Now what we are doing is VDS is less than twice the VGS minus VTH if this is a condition where you are operating your VDS value. So now VDS value is very close to 0, or you can call it as VDS value is twice the VGS minus VTH. If that is the case, then what you can do is that you can write the current expression, or current expression can be modified, and you will get the current which is equivalent of mu n COX W by L VGS minus VTH into VDS, right? Means you discarded the second term, only you have the first term. Now if you look at this expression carefully, then which is equivalent of, so you can consider that this expression is equivalent of I into R into, which is equal to I is V by R, something like this. Means current is proportional to the voltage that you are applying. Okay, means that is your linear variation, right? And this is what the region where you have a more linear variation of your drain current that you can notice. Whereas as we are moving away from this region, then you can see that instead of linear, it is getting little modified, not exactly linear. You can say that it's a kind of non-linear variation that you can notice. So what you can write it here is that the ID, which is equal to two term, one is this first one. So you can write it as this is my first term and this is my second term. So what you can write it is ID, which is equivalent of VDS by R on, right? So what you can write it here is R on, from this R on, which is equal to half 1 over mu n COX W by L into VGS minus VTH. So this is referred to be a linear resistance of your device, or you can call it as a on resistance of your device. And we use this on resistance when we were discussing our digital circuit. So your NMOS or PMOS is equivalent of a resistor, right? While discussing your inverter characteristics, resistive load inverter, depletion load inverter, and then CMOS inverter, we made NMOS or the PMOS transistor equivalent of resistance. In fact, in our NAND gate and NOR gate also, we considered that NMOSs and PMOSs are equivalent of on resistance. What you can consider here is that your MOS transistor is acting as an electronically adjustable resistor, and it depends on the value of VGS minus VTH. What you can call it as, this MOSFET acts as electronically adjustable resistor, because its resistance value can be varied by varying the value of your VGS minus VTH. As VGS minus VTH value is lesser, your on current is higher. Sorry, on resistance is higher, and you can tune the resistance value by varying this parameter. Okay. So what you can write it is that the MOSFET can act as a voltage dependent resistor or electronically tunable resistor as voltage dependent resistor for the condition where VDS is twice the VGS minus VTH. So VDS must be less than twice the VGS minus VTH value, then it acts as your variable resistor. Okay, so sometime we are going to using this resistor. Okay, it means we have taken the linear current expression, and from there we extracted the on resistance of your MOSFET, and because of that you can call it as MOSFET acts as a voltage dependent resistor, and the condition is that VDS value is less than VGS minus VTH. Now if you take the saturation expression of your MOS transistor, then let me draw the complete graph of MOSFET when it is in linear and saturation region for a one value of VGS. Then it is going to be something like this. VDS on your x-axis and then ID on your y-axis, and as you increase the VDS value, then it linearly increases as the VDS increases, and then it goes to saturates, and finally you can notice that the constant current, and this is the point where you can say that the constant current. So here it is VGS minus VTH, and this is what the constant current that we already written the expression for it. Okay. Now when it is acting as a constant current, so this is a region where you can call it as a linear, and this is a region where you can call it as a saturation. Okay, so we had seen this MOS transistor in linear region of operation, and it acts as a kind of variable resistor. Right? What is going to happen if you operate your device into the saturation region of operation? Okay. So for this plot, what you can say is that if you take a MOS transistor here, which is going to be something like this, this is your MOS transistor, right? This is a gate terminal, drain terminal, and then source terminal. You're going to have gate to source voltage and drain to source voltage, and the source terminal is common for gate and drain terminal over here. And when your VDS value is less than VGS minus VTH again, then you have a linear, and that case when you talk about the gate voltage and the drain voltage. So now you can consider this is my gate terminal, this is my drain terminal. Now you relate this gate terminal and drain terminal potential. Now here gate terminal is having a much higher potential than the drain potential, which is equivalent of VTH, and that VTH is much greater. It means gate terminal is having a much higher voltage than your drain terminal in your linear region of operation. Okay. Now coming to this point where the demarcation line of saturation and linear, at this juncture, if you draw your MOS transistor again here, this is a drain terminal, this is the drain terminal, and then this is the gate terminal, and source is common for both. Now, and the condition here is that VDS is equivalent of VGS minus VTH, right? Means at this point. Okay, at this point, what you can see that the gate voltage and drain voltage, gate terminal voltage and drain terminal voltage, which is exactly equivalent of your VTH. Whereas in the previous case, gate terminal voltage is much higher than your drain terminal voltage, which is much greater than VTH. Whereas in this case, gate terminal voltage is exactly higher than the threshold voltage of your device in comparison with your drain terminal voltage. Okay, coming to the another point where Someone is recording this session. Now I can consider this another region of operation where it is under saturation, where this is my gate terminal voltage and this is drain terminal voltage. This is the gate and drain. Now the condition here is that VDS is much greater than VGS minus VTH. If this is the case, then what is going to happen is that your gate voltage is less than the VTH voltage. Okay. So these three are the different mode of voltages at gate and drain terminal of your transistor, from 0 to higher value of your VDS, because as you see from the plot, it is going to be increases in the linear stage and then becomes saturates when your VDS value is much higher in comparison with your overdrive voltage. So VGS minus VTH can also be referred as overdrive voltage. Okay. Now, if we consider only the saturation, because we already discussed about the linear, in saturation region of operation, what you can indicate as a MOS transistor is that now I can draw my MOS transistor here. It's N-channel MOSFET. Now we apply the gate voltage to create the channel, and we have a drain voltage to make the device in linear saturation region of operations, right? And here, instead of this symbol, what you can write it here is that VDS value, which is this one, and this is your VGS value that you need to apply the gate terminal so that channel can be created. And because of this IDS, then you have the current called as VDS, you have a current IDS. Now what you can see is that now you want to represent this MOS transistor as a two-terminal device. It means you are equating this MOS transistor behavior as a two-terminal device behavior. Okay. With the gate voltage, of course, it is greater than threshold voltage, and your device treated to be under saturation region of operation. Device is under saturation region of operation, and now you can replace this entire MOS transistor as this one is equivalent of two-terminal device as a constant current source. Okay, so which is referred to be your ID. Okay. Now with this, what you can say is that you can make an equivalent model for this transistor, and you can say that the equivalent model is going to be something like this. Now we have a gate terminal. This is gate, and source terminal, which is common for the drain and source. Now here we are indicating the drain terminal, and this is a gate which is common for both source gate and drain terminal. And we apply the gate to source voltage, which is VGS, to make the device in cutoff for linear and saturation. It does not depends on that value actually, but it depends on VDS also. So VGS, the purpose of VGS is to alive the device. So VGS value is to create your inversion layer, right? Now with this, what is going to happen in your device is that your drain terminal is becoming a current source, which is constant current source. And if you write the current which is in the saturation region of operation, which is mu n COX W by L VGS minus VTH whole square, right? So this is your source terminal. So you can write it as three-terminal device, but here we made equivalent of this MOS transistor entire with gate voltage as a constant current source. Symbolically, you can represent this way, and your current ID is going to be something like this. Okay, which is written as this equation, right? So previously, your MOS transistor is acting as a variable resistor. Now, this case, your MOS transistor acting as a current source. Okay. Now, what we are going to do is, now if you are interested to design a current source, let's say an example here. If you are interested to design a current source, and then I need a current source of 1 milliampere. Okay. So what you can write it here is design a current source, and that current must be of 1 milliampere. In the constant current source, right? So it should give the constant current which is of 1 milliampere. And for that, you need to know some of the parameters of your MOS transistor, and this is the expression which is known to you. So in which you have to know the mu n COX value, W by L value, right, and VTH value. And here we are giving the mu n COX value. Mu n COX is assumed to be 100 milliampere per volt square. It's not milliampere, you can consider it as a microampere per volt square. That is mu n COX value, because mu n is a mobility and COX is a capacitance of your device. When you have a transistor as a circuit engineer, you do not have a variation in your mu n COX, which is something played by the device engineer who can play with COX value and can change the mu n COX. So as a circuit engineer, you just accept the value of mu n COX defined by the technology node. Right? And then W by L value. So here you can take any value of W by L, depends on the technology node. Here you can consider the W value is 5 micrometer and L value is 0.5 micrometer. Okay, assuming to be a longer technology node, and VTH value is assumed to be 0.5 volts. Now we need to make the current ID, which is equal to 1 milliampere. So, and we are aware of the expression of your ID, which is ID equivalent of half mu n COX W by L VGS minus VTH whole square. So now you are aware of the sum of the parameter. ID is known, which is given as 1 milliampere. 1 milliampere is given. Half mu n COX value is given, which is 100 microampere per volt square, and W by L, which is 5 micron by 0.5 micron. So it turned out to be 10, because micron get cancelled out. 5 by 0.5 is, which is equivalent of 10 into what is the value of VGS minus VT? VGS minus VTH is given as 0.5 volts whole square. So from this you can easily calculate the value of VGS, which is equivalent of 1.9 volts. Okay. So now we are getting the value of VGS is equivalent of 1.9. Now what you can do is you go back to your MOS transistor here. Let me construct it again. So here, if I construct a MOS transistor, something like this, and this is my VGS value, right? And here it is VDS. Now this VGS is going to be 1.9 volts. That is already extracted, and this current we are expecting that it is 1 milliampere. Okay. How do you ensure that this current which is generating by fixing the value of VDS is equal to 1.9 volts is a constant current? What I am trying to say is that the current which you are trying to generate as a constant current of 1 milliampere is going to be same by making the value of VGS is equal to 1.9 volts. So how do you verify here or ensure it? You can be assured VDS value should be greater than VGS minus VTH. So first identify the value of VDS so that you can say that whether the design is right or wrong. A VDS value which is greater than VGS is 1.9 volts and VTH is 0.5 volts, right? And which is equivalent of 1.4 volts. Now if your VDS value is greater than 1.4 volts, then it generates a constant current of 1 milliampere. Right? Similarly, if you want a resistor value in case of linear, then you can get the variable resistor or a fixed value of resistor by fixing the sum of the parameter in the R on expression, so that you will get resistor value. Here we are trying to make constant current of 1 milliampere from the transistor. Okay, how we have started to design? We extracted the sum of the device parameter which is given to us along with the current which is required. So we extracted first VGS value and connected it to the MOS transistor gate to source terminal in between, and we ensured that VDS value, so VDS value is supposed to be higher than 1.4 volts, then this device acts as a constant current source. Right? Now the second case. Right, so we have taken this constant linear region and then saturation region of operation of your device. We'll talk about little bit channel length modulation factor and how the channel length modulation is going to be incorporated to the equivalent model of your transistor, right? So if I draw a MOS transistor, cross-sectional diagram of a MOS transistor, then it is going to be something like this. So here we have n plus region of source and n plus region of drain, on top of which you're going to have this oxide layer, gate oxide, and gate on top of it again. So here you make the gate, right? What we are trying to do here is that we talk about channel length modulation in terms of expression. So first you just take a MOS transistor here, and then you try to make it as, you try to bias it. So here it is VGS positive negative, and here it is VDS positive and negative. And this is your N channel MOS transistor. So you are applying this gate to source voltage here and drain to source voltage. So drain terminal and gate terminal. So let me connect those terminal here. What I'm going to do is I'll connect my gate to source voltage here. This is VGS positive and negative, and here it is VDS positive and negative. And this is our MOS transistor. So when this gate voltage is higher than threshold voltage, then what you can say is that here you have a channel. It means here you have a carriers, right? So this is your channel region where you can see the enough amount of carriers. Or from our old discussion, how do you create inversion layer? Inversion layer is created by applying a gate voltage so that the opposite carrier concentration is equivalent of the bulk carrier concentration, right? So here your bulk region is of p type. The electron concentration is equivalent of your bulk concentration. That is what the voltage you have to apply so that the electron concentration is equal to bulk concentration. And considering that factor, here you have, this is the channel length of your device. And as you increase the VDS value, a channel is formed and you are increasing the VDS value more and more, then what is going to happen is the channel gets pinches off. Instead of channel from this point or ending of your source region to starting of your drain region, which is referred to be L, so 0 to L region, it becomes smaller. Okay, how it is becoming smaller? So it can be more clear by writing the expression of this current. So I can write it as your VDS value increases, then what is going to happen? The channel gets pinches off, and then net channel length is becoming this one. So instead of L, now what you can see is that only from L to L prime, because channel gets pinches off here, and essentially what you can see is that the carrier is going to here. So it is because of the drain voltage that you are creating at the vicinity of your drain and channel region. Okay. So here channels electrons are there from this point, and because of the higher drain voltage, this electrons getting attracted in this region. But you can see that here there is no concentration of the carrier available here. That is the point that will be noticed here. But carriers are available up to this point from L is equal to 0 to L prime. Okay, from L prime to this drain region, channels carriers are getting attracted very fast, and you have a current flow in your device. Okay, so if you write the expression here, ID, which is equivalent of half mu n COX, because we are talking about the saturation region of operation, W by L, VGS minus VTH whole square, right? Now what we are doing here is that we are increasing the drain voltage, right, by which your channel, instead of L, now it is becoming L prime. It means L prime is lesser than L. So now this is becoming smaller value, right? So this L parameter, which is then in your current expression, which is becoming smaller. So as L becoming smaller, then what happened to your current? because L at the denominator of your current expression, L becoming smaller, your ID gets increases. And that's how your current is starts increases instead of constant. Okay. Now, if we write the current plot here, this is VDS and ID. What you assume is that when the current gets saturates, and then it is supposed to be constant, but instead of that, it is going to be increases, something like this. It is because of decrement of your, this variation is this variation here. You can see that colored line. As it is ID increasing, then you can see the more variation here. The difference here is because of the decrement of your L value because of pinch off at the drain region. Okay. So due to which what you can do is you just make an expression of this device. So we'll write the same expression here again. ID, which is equals to half mu n COX W by L, and L is becoming smaller here, VGS minus VTH whole square. The same expression need to be validated, plus into 1 plus VDS value is there. So if VDS value is, what you can say is that not so higher, then what you can do is that you will get the only second, the first term, which is 1, and remaining term gets neglected, and there is no impact on your current. But as VDS value is increasing, and that VDS value causing to be decrement of your L and increment of your current I, so that what you can do is here you add a term called as lambda, and this lambda is referred to be channel length modulation coefficient. And the unit for this channel length modulation is, let's say here this is 1, and now you can notice this term 1 plus, and here you have voltage. Now you take the unit of this lambda is 1 over voltage. Voltage will get cancelled out, and then this is a constant term. So here the units of lambda is 1 over volts, and you can call it as channel length modulation coefficient. Okay. And due to which now what you can see is that the model, equivalent model of your transistor is going to be something like this. Now source is common for both gate as well as the drain terminals, right? So here you have a VGS value to create inversion here, gate terminal. Now you have a current which is half, and this is the drain, half mu n COX W by L VGS minus VTH into whole square into 1 plus lambda times VDS. Right? So this extra term is getting added here in comparison with your previous constant current source equivalent model. Okay, so this is again source terminal. Now with this basics, let's start building an amplifier. So we are trying to build an amplifier using these concepts, like when it is acting as a constant current source and it's a variable resistor, channel modulation factor need to be taken into account when the channel gets pinches off, right? So with this background, let's try to make an amplifier. Build an So let's try to build an amplifier. So for that, what you require is that, let's say from your basic electronics engineering course, BLE course or EDC course, you must be aware of the small signal equivalent model for the mass transistor and BJTs. So what I am going to do right is here is that here I have a V1 voltage, positive and negative terminal here, and because of that there is a current which is constant, and that current depends on the K factor and the voltage that we are applying here, V1, and along with this there is a load resistor in your circuitry which is called as RL, and now here we have a V out voltage, positive and negative, right? And that V out voltage is expected to be minus K times RL into V. and this V is a small signal input that you are trying to apply, and that small signal input we are applying at this junction. So this is your V in positive and negative. It means an amplifier which try to amplify the signal which is applied to an input side, and then output side you want to amplify it as it is given, and here the negative sign indicates there is a output, the output which is going to be shift 180 degrees, and that's the reason we are using the negative sign here. Okay, so because of V1 there is a current in your device which is K times V1 and then load resistor RL, and which gives you the output voltage V out, which is equivalent of K times RL into V1. Okay. Now what you can write it is that V input that we are applying is a small signal and it is having an sinusoidal. So you can consider that this is kind of a mic or small signal. So when we try to speak, then you have a signal and we are representing it as a sinusoidal one, but the speech signal that we normally consider is not exactly a sinusoidal wave, but time being just accept it as like it is a sinusoidal signal, something like this. And amplitude of this signal is 50 millivolts on the positive and negative also 50 millivolts, right? Now this 50 millivolts of sinusoidal signal that I'm talking about here has a small signal, and this need to be amplified at the output of your transistor. So here we are trying to use a MOSFET, and that's supposed to be amplify the small signal that we are applying, and that gets amplified. How much it is? K times RL into V input. Okay. So to do that, what we are going to use it, let's say MOS transistor, MOS transistor we have to use. Okay. So if I draw a MOS transistor here, so straight away I'm drawing it as MOSFET and connecting it as something like this. This is a load resistor, and this is treated to be a V out that we are trying to measure. So this is a gate, terminal, drain, and source. Now the input that we are talking about is an audio signal, and that audio signal I'm connecting it through a mic. So I can consider this as a mic which is connected something like this. So I can write as a mic symbol here. This is what a mic which is containing this signal. So this is a signal that you have in a mic which is 50 milliampere signal that you are trying to apply, and then you need to notice that output is equivalent of higher value, right? Now this is what the signal that you are trying to applying to your MOS transistor here, gate to source voltage. This is referred to be VGS value, right? Now if you draw a ID VGS plot for your MOS transistor, this is a VGS axis, that is X, and this is ID which is Y axis. Now as you apply the gate to source voltage, and then you can see that there is a current variation in your device, and there is a point where you can see that there is a threshold voltage of your device. What is the input voltage that you are applying here is, the input voltage that we are applying here is the 50 millivolts, right? And that 50 millivolts is somewhere here because VGS value. So do you have any VGS value here, DC value here? So VGS, gate to source voltage, is essentially treated to be 0 at 0 voltage of this point of VGS. Now you are applying a 50 millivolts. So this is a small signal which is 50 millivolts going from this point to this point. Minus 50 millivolts here and plus 50 millivolts here, right? And then what is the current because of this signal that you are trying to notice? Because that amplification takes place here as a K times of V1. So when you have this K times of RL and V, and that's how your signal is getting amplified. Okay, so if this factor is more, then you have more amplification. So you required K value should be as high as possible, and you required of course RL value also. Okay, now what is the current that you are trying to obtaining from this? Here, the device is treated to be off. The MOS transistor is off because you haven't applied any gate to source voltage, and you applied only analog signal, which is 50 millivolts, and this 50 millivolt signal is not sufficient to make your device on. It means you haven't created any channel region over there, because gate to source voltage is 50 millivolts. It doesn't create a channel, and that your analog signal, right? So you are biasing somewhere here, and which doesn't create any amplification in your output, right? And here threshold voltage of your device, you can consider it is 0.5 volts. At 0.5 volts of threshold voltage, your channel is getting created, and then device acts as a current source. When you are using it as a saturation region of operation, then signal gets amplified. But here, the gate source voltage is less than threshold voltage, is clearly indicating this from graph that your input voltage is plus or minus 50 volts. But it is not close, not even close to your threshold voltage of the device. So MOS transistor itself is off, and it doesn't amplify any signal, right? So you require a certain voltage. That voltage makes your device alive. Here your transistor is dead completely because there is no channel, and without channel and device is in off, you cannot amplify the signal, right? So this is treated to be one kind of attempt by which we could not get the signal getting amplified. Okay, this is the first attempt this is the first attempt in which what we have done is we connected our analog signal directly to the MOS transistor without any biasing voltage to this, and we are trying to estimate the output over here because the input voltage directly we are connecting as an analog signal, which doesn't make your MOS transistor into what do you call saturation region of operation, and device is treated to be off completely, and then there is no amplification of your output voltage. So first attempt is not an appropriate one, so that we need to search for an alternative attempt so that we can make amplification of our output. So this is the first one, our first attempt, that you can say that this is the first attempt we tried, and then we are unable to success the output should be amplified version of your input. The second attempt, what we'll try to do is we'll take the same setup but little modify it. Okay, so let me redraw this MOS transistor structure again here. This is V out, and here what we'll do is, let me consider this is a negative point. So here we connect our mic, which is of 50 millivolts. So let me write it as like something like this, 50 millivolts. And along with that, what we'll do is we try to connect a DC biasing, a certain voltage. And this is called as some voltage, and that voltage is equivalent of the threshold voltage of the device. Okay, now it is not so high, with just equivalent of the threshold voltage of the device. Okay, what we have done is that we have an analog signal which is superimposed on the DC signal. This is what the setup that we are trying to create at the input side. In comparison with your previous figure, we just added a DC biasing over there, and our analog signal is superimposing on the DC, and remaining things are same. If this is the case, then what is going to happen here? Okay. And we are expecting that the output should be 10 times higher than your input signal. So here we are applying the 50 millivolts as an input, and then it must be 10 times higher than the input voltage. That is what you can say that the amplification is done. It may be 2 times or 10 times. This amplification factor is as high as possible, then the amplification of your transistor is better, right? So you require, we assuming that we are expecting the 10 times of amplification of your input signal, right? So if this is the case, and then here you are try to draw the output waveform here, and this output waveform is exactly 180 degrees opposite of phase. That's now we had seen from the previous graph. So here we are applying this input, and correspondingly you're going to have the output something like this, which is 180-degree phase apart from the input signal, right? And just calculate the current here, and then what is the resistance value, load resistance value required to get the 10 times of amplification of your input signal. So from the previous calculation, to design an amplifier, to design a constant current source to get 1 milliampere of current, we have assumed that mu n COX is 100 microampere per volt square. Same parameter that you can take it again, W by L, which is equal to 10 times, and then VTH of the device is equal to 0.5 volts, right? With this, if you calculate the value of ID, so this ID is going to be half mu n COX is 100 microampere per volt square into 10, right? Into here VGS is exactly equivalent of VTH plus 5 millivolts, right? So the input that you are applying is superposing your input signal and then DC biasing. So here this complete input VGS, you can write it as, which is 50 milliampere, 50 millivolts plus VTH signal that you are applying is equivalent of VGS. So now VTH is already there, and now you can consider that VTH plus 50 millivolts minus VTH whole square, this to gets cancelled out, then you end up with 50 millivolts square, and finally you will get the current ID, which is equivalent of 12.5 nanoampere. Okay, right? So here you have a current ID of this one. So this is a current that you can notice that ID, which is of 12.5 nanoampere of current, right? Now with this current and output voltage that we are talking about is that how much we are expecting the output voltage is a 50 times of your input. So you can consider V out is 50 times nothing but, sorry, 10 times nothing but 50 millivolts. So if you want to calculate the value of the load resistor RL, which is equal to V out by ID, which is equivalent to, what is V out, 50 millivolts divided by ID is 12.5 nanoampere, and it turned out to be the resistance of 4 mega ohm. Okay, so now if you have a resistance value RL which is equal to 4 mega ohm and your input signal of 50 millivolts, sorry, 5 millivolts, not 50 millivolts here, it is just like a 5 millivolts. It is 5 millivolts, but output is 10 times, so 50 millivolts output, and input is 5 millivolts. Okay, so when your input is 5 millivolts and then output is 50 millivolts, to get this much of amplification, then you require the load resistance value of 4 mega ohm, right? So here what we have considered that the amplification factor of 10, then RL value here we required is 4 mega ohm, so that we can able to amplify the signal 10 times, right? So this RL value required is pretty high. Okay, and we are well aware that IC technology is not recommending to use a resistor in IC fabrication along with your MOS transistor, because this resistor generate lot of heats and which causes to be malfunctioning of your entire IC, and that to the resistance value is pretty higher, and which is not at all recommendable or suggestible to go for amplification something like this. And the condition here what we followed is that our analog signal, which is an input signal from mic, which is superimposing on the DC voltage, and that DC voltage is equivalent of exactly threshold voltage of the transistor, right? Now what we'll do is, the previous what we have done in the previous case is that we haven't applied any DC biasing here, but in the second attempt we have applied a DC biasing which is equivalent of threshold voltage. Now we further increase the DC biasing condition. It means we are superimposing on your you are superimposing analog signal on digital, right? So let me take some value of my DC biasing voltage, and this is considered to be attempt 3. This is MOS transistor that we are talking about so far, and load resistor RL. This is V out that we are expecting. Now here we have what you call 5 milliampere, sorry, millivolts of audio signal, and this is V naught. We are not defining what value it is, but it is greater than VTH, higher value than your VTH value, right? So if we draw a plot here, this is VGS and here it is ID. So when it is VGS is increased, then you can notice this is what the current, and this is the point where you can call it as a VTH. The previous case we have applied that, but now what we are doing is we are applying a voltage called as V naught, which is higher than the threshold voltage value, right? Now if you operate here as a DC voltage, and then correspondingly you have some current which is referred to be I naught current, right? Previously with applying VTH we have calculated some current, and that current is very less amount of current that you can notice from the graph. So here if you draw it, right, so this is ID and VGS. Now exactly the threshold voltage of the device that you are applying this point, the VTH. Now as you apply this, then there is a current increment in your transistor, and that current is very less value, and it is 12 nanoampere of current that you can talk about here, right? And that too, here you have your analog signal that is going to be this point to this point, because it is 5 millivolts, left side of this and right side of this, because positive and negative, positive half cycle and negative half cycle of, and which is sitting on your VTH value. So with the higher side, what you can say that there is a small amount of current because of this VTH value. But whereas at this juncture, it is much higher than this VTH value, which is V naught, and because of that, there is a variation in your output. Now here, if I have a signal something like this, which is 5 millivolts on the positive and then 5 millivolts on the negative, then you can see the more amplification of your signal, right? At this juncture, we are assuming that naught is equal to 0.9 volts and VTH is same as the previous one, which is 0.5 volts. If this is the case, then what is going to happen? These are the points where you can notice that right. So this is your analog signal that you are applying, which is sitting on your DC, right? So this is what the part that we are talking about here. So the DC signal, analog signal is sitting on your DC, and which applied to the transistor, and we are trying to amplify this signal, and we want to notice that whether it is amplified or not. Okay. And so this is a point which you can call it as an operating point. So this is a point is referred to be an operating point. Okay. Now if you calculate the current here at V naught, so when you apply the V input, which is equal to V naught value, then you have the current called as ID naught, which is equivalent of half mu n COX W by L, right? And this is 0.9 because you are applying V naught. VGS is equal to V naught is 0.9 minus 0.5 whole square. Is exactly at the operating point, ID naught. Means that without applying any analog signal to that, so what we are trying to estimate here is what is the current that is available without analog signal, right? So here what you can say is that this is a point where we are trying to estimate the current. This is a point which indicates the ID. This is ID naught current, right? Means at this point. Okay. And if you substitute all these value, mu n COX value and W by L value from the previous parameters, you will get it as 80 microampere. In earlier case, what we obtained was 12.5 nanoampere. And when you apply the what you call DC as well as the analog signal together, then you are going to have ID1, right? So this is treated to be ID1, which is equivalent of half mu n cox w by L, remaining thing same. And here it is analog plus DC 0.905 minus zero point 0.5 whole square, and it results into 82 milliampere, right? So from V naught to ID naught to ID1, there is a variation in the current of 2 microampere. Okay, 2 microampere current is there. So change in your ID, which is equal to 2 microampere. At DC point, you are going to have 80 microampere of current. With DC and analog signal, you have the 82.5 microampere of current, right? So the current that you are trying to notice here is that this is ID current because of this analog signal, and which is of 2 microampere. Okay, and what is the output voltage that you are expecting, which is 50 millivolts, because it is 10 times. We required that it is 10 times higher than the, so it required to be 50 millivolts. So here this value we are expecting that 50 millivolts because we applied the analog signal of 5 millivolts. So to get that, then what is the resistance value required? So RL value required, which is equal to V out, which is 50 millivolts divided by 2 microampere of current. So it is turned out to be 25 kilo ohm, right? So here the resistance value is 25 kilo ohm. In case of previous attempt, we got the RL value is equal to 4 mega ohm. What it can notice, what we can notice from these three, what you call attempts, is that without any DC biasing, then you cannot get any current in your device. Means you will get zero current, right? So here you will get zero current here because there is no device is here, the device is not alive even, and so you will get the current is equal to zero. And in case of second attempt with DC biasing of threshold voltage, so you will get some finite amount of current, and which causes to be requirement of larger value of load resistor, whereas your biasing voltage is further increased greater than threshold voltage, then you require the lesser value of resistor to make the amplification of your input signal. When you opt for a vehicle such as car or other vehicle which can move with higher velocity, just like as you are increasing the biasing voltage higher and higher, then what you can do is that you can reach with a higher velocity vehicle, you can reach much faster, right? So as you are increasing the biasing, then your load resistance is becoming smaller value and your current is becoming higher value, so that you can design better amplifier. But all together what you can notice is that you require a DC biasing. So this is called as requirement of biasing. So in some of the interviews, people may ask you the question like, what is the requirement of a biasing? Biasing is required to amplify a given signal, okay, to make a device on or It gives the ability to the transistor to amplify, or it gives a strength to the transistor to amplify effectively, so that you require a biasing. Okay, so these three attempts will give us that biasing is important criteria, so that you can bias a transistor which is greater than threshold voltage or above the threshold voltage, so that we have a higher in a current and lesser the requirement of your load resistor to obtain a desirable amplification output. Okay, to get required amplification output, what you have to do is you should make your biasing in a proper voltage, with a proper voltage, so that you will get the better amplification with requirement of less load resistance. Okay. Yes. Now, what you can conclude from this discussion is that you required a biasing. Okay. So what you can notice here is that what you can notice that biasing is essential for amplifier, right? And what other point to be noted here is that the first point you can notice is that a MOSFET converts a voltage, because you are applying a voltage, to a current. So it converts voltage to current, right? Because if you notice this point clearly here, that when you are applying the gate voltages here, so you can notice this, when you apply a gate voltage, then it is converted into the current, right? So you can call it as, it is a voltage to current converter. So what you can write it here is that, so you have a MOS transistor and this is voltage to current converter, voltage to current, right? And you call it as transconductor. Okay, voltage to current converter is also referred to be a transconductor. Okay. Now, second point is observed is that we are trying to biasing your transistor, but what is the value of V naught that we need to fix it? Okay, so here we are increasing the value of V naught, which is beyond the VTH value. Then I can go for a higher value of VTH, or I can go for very close to VTH value, which is a suggestible value for V naught, so that we'll get better amplification. Now, if you have a V naught value here, yes, as you can observe from this point, let me redraw it again here. This point, so let me consider this is V naught, and correspondingly there is a I naught current. So of course this is your ID, this is the VGS, right? At a V naught value, without any analog signal applied to your microphone, right? Without your any analog signal, with V naught voltage, it causes to some current in your device, right? So what it means is that you have this device, something like this, and here you have a microphone and then DC voltage, which is referred to be V naught, load resistor, and V naught value. So here you have some current I. So what can be noted from this observation is that when you have some V naught value, at V naught value you have some current ID, and this value is higher, then you can notice that here you are going to have a higher current. So V naught 1 and V naught 1 here, so you can get I naught 1 here. As it is higher, then without any analog signal that you are superimposing on your DC, it gives some current. As it is as it is generating some current, then if your amplifier is operating with some battery operated devices, just like my microphone. If I speak it, or some people use a microphone when they are in the class, and that they're normally operating from the battery, then without any analog signal, it continuously takes some current, and that current leads to be the battery consumption. So as you're increasing more V naught value, it leads to be a dropping of draining of your battery very fast. Okay, which is not suggestible choice to pick the value of V naught. Okay, it should not be so close to V naught. It should not be so close to VTH value. So let's say here it is VTH. As it is away from your VTH, V naught is away from your VTH, then you have certain current. As it is increasing further and further, then you have corresponding current I naught and I naught 1. This I naught and I naught 1 causing the, what do you call, power dissipation from your battery, power consumption from your battery, and which results into battery is going to die very fast. Right? So as you are expecting that amplification should be required as high as possible, but you, at a cost of reduction of your battery life. Okay. So this point to be taken into the care while you are applying your biasing voltage. Right. So this is another point that should be keep in mind. So here,
can you repeat the last point?
Sorry.
Can you repeat once last point, second point?
Yes, when you are increasing the VGS value higher and higher, and here VGS is referred to biasing voltage, and you are superimposing your analog signal on your DC biasing and applying to your transistor so that it can amplify, right? As you increase the higher value of your biasing voltage, that is your VGS value, then it causes to be current flowing in your transistor as it is away from your VTH value. As you have more value of V naught or higher value of V naught, then correspondingly you have higher current in your transistor, and this current which causes to be power dissipation in your power consumption from your battery, because you have a microphone and that microphone is getting the signal, getting the power from your battery, because when we have a microphone with a collar microphone, then that's supposed to be connected with the battery. So you have a as you have a higher value of VGS, then that higher current takes place in your transistor, and which makes a device is going to be die very fast, or battery life is going to be decreases as higher value of VGS that you can keep. But lower value of VGS is close to VTH doesn't help us to amplify the signal as we require. So while deciding the value of biasing voltage, you should keep in mind that what is the actual value that required as per the requirement. It should not be so high, it should not be so low. So high means it is not much higher than the VTH value, and it should not be very close to the VTH value. That is in the mid range of the two extreme levels. Okay. Now we'll see the transconductance of your MOS transistor. So transconductance normally referred to be a GM. Okay. So if we draw a plot here of ID VGS, this is VGS and ID. Okay. As your VGS value increases, and correspondingly you have this variations. Okay. And GM, we are aware that change in your drain current with respect to change in your gate to source voltage, dID by dVGS. So what is the amount of change at the drain current with respect to change in your gate voltage, and that will give you the transconductance, right? So, and the GM is indicating over 1 over ohm, okay, or inverse of ohm. You can call it as Siemens, and the symbolic representation is capital S, right? So when we consider a current here, ID, which is equivalent of half mu n COX W by L, and it is under saturation region of operation, right? And correspondingly, what you can see is that the GM value, okay? The GM that we want to write is del ID by del VGS. What you can notice is that here, which is mu n COX W by L VGS minus VTH. If you do that, what you can get is mu n COX W by L into VGS minus VTH. Okay, so how we are obtaining this? Let me draw a transistor here and then see what is the current that we are trying to talk about. So let me take a MOS transistor, N-channel MOSFET, and here it is under saturation region of operation. The condition is VDS is greater than VGS minus VTH, and ID current, which is written as ID, which is equals to half mu n COX W by L VGS minus VTH whole square, right? Now, what you can see here is that GM, right, up to gate voltage, the up to threshold voltage of your device, there is no current which is indicating in your graph. So as VGS is less than or equal to VTH, there is no current in your device, right? And if you differentiate it, then what you can see here is that you have the current in your transistor, and correspondingly, if you want to see the change in the current with respect to change in the voltage, which is del ID by del VGS, which is referred to by GM, is if you differentiate with respect to VGS, then what you can see is a square, then 2 times of that, and 2.5 it gets cancelled out, which is equivalent of mu n COX W by L VGS minus VTH, right? So VGS minus del VGS by del VTH. So only VGS is there, so del VGS by del VGS becoming 1, and then you will end up with this term. So this is referred to be one of the expression for your GM. What it indicates? What transconductance indicates? This indicates that, or it defines that how strong a device to convert your voltage into a current. Okay, this transconductance indicates how the device is strong to convert voltage into current. So this is what the implication of your mass implication of your transconductance function. Okay, now we'll see some other expression for your transconductance, which is this can treated to be a first expression, and then second expression can also be written as, now you have ID, right? So this is the previous expression of ID. So what we can do here is that if we replace VGS minus VTH, so I can consider ID, which is equals to half mu n COX W by L VGS minus VTH whole square. What we are going to do is, both the side, if I multiply with 2 times of 2 over VGS minus VTH, okay, I multiply with this 2 factor, which is 2 by VGS minus VTH, then what we're going to get is the 2 times of ID over VGS minus VTH, which equivalent of, so 2 and half gets 2 multiplied by half, which is going to be cancelled out, and then you will end up with mu n COX W by L VGS square at the numerator, whole square at the numerator, VGS minus VTH at the denominator. So you will end up with 1 VGS minus VTH, and we already extracted that this is equivalent of your GM. So second expression of GM can be written as GM, which is equivalent of 2 times of ID, that is what we are getting here, divided by VGS minus VTH. This is another expression for your transconductance, right? So if you look at this second expression, then what it indicates that if you want to increase the GM value, then you just decrease the VGS minus VTH value or increase the ID value. From the first expression, what you can notice is that to increase the GM value, that is amplification, right? That is the strength of your transistor to convert your voltage into current, right? That is the strength. So as you require the GM value should be as high as possible to make GM higher, then you have two terms in your first expression. The first one is your W by L and second one is VGS minus VTH. Assuming that VGS minus VTH is constant, and then you can increase the W by L of your transistor so that GM can be increased. Or else W by L is made to be constant, you can increase VGS minus VTH so that GM can be increased.
Time is up.
Wait for a minute. Okay. The last one, the third expression for your GM, which is GM is under root 2 times mu n COX W by L into ID. This is the last expression that can write it, right? So these three are the normal transconductance expression used in our upcoming classes where we talk about transconductance of your transistor. Okay, so what you can notice from these graphs, from these three equations of GM is that, so for first one, GM is proportional to W by L with VGS minus VTH as a constant, and the other one is GM is proportional to VGS minus VTH provided that W by L is supposed to be constant. Whereas in the second attempt, that GM is proportional to 1 over VGS minus VTH and provided that ID should be constant because of the ID at the numerator part. So this is at the numerator part. If it is constant and you decrease your VGS minus VTH, then you can increase the GM value. Other case is that you increase the ID by making VGS minus VTH. So one parameter is interrelated to other, or else you can increase the GM value by increasing your ID by making W by L constant. Okay, or else increase the W by L value by making ID constant and you can get increment in your GM. Okay, so this is all about your transconductance of your MOS transistor, and we start trying to build different single stage amplifiers with these concepts. Okay, so we'll stop the session here and then we'll meet in the next class. If you have any queries related to today's talk, you can raise. Okay, then we'll stop the session here and we'll meet in the next class.
Thank you, sir.
Thank you, sir.